Good
Good
morning,
morning,
class.
class. I am teacher Shikaine.
I am teacher Ryan Pilago,
I am Isa Temple.
and
And
today
today we
we
are
are going
going
to
to discuss
discuss
the
the
construction
construction
of
of
real
real
numbers,
numbers,
the
the
set
set
of
of
integers,
integers,
and the
and the
set
set
of
of
rational
rational
numbers.
numbers.
Okay, good morning, students. Okay, before we start, may I ask the class mayor to please lead us in prayer. Amen. Okay, so good morning, class. Okay, so before taking your seats, kindly check if there are pieces of papers and cellophanes under your chairs, and please arrange your chairs. Okay, so let us check your attendance. So, class secretary, may I know who are the absentees for today? Oh wow, it's nice to hear that there is no absent for today. Okay, so how are you guys? Are you all good? Alright, very good. Okay, so before we proceed to our lesson, I have a classroom rules that must be followed. Okay, so first, listen and be quiet when someone is talking in the front and sharing his or her idea about the lesson. Second, use positive language and positive attitude, avoid swearing. Third, be respectful of others' ideas, respect one another. Did I make myself clear, class? Okay, very good. So last meeting, we have discussed about the continuum hypothesis. Who can tell me what is the meaning of continuum hypothesis? Okay, Ryan. Very well said. Good job, class. I am very much delighted to hear and know that you have understood and learned from my class last meeting. Okay, so listen carefully. Before I will formally introduce our next topic, we will have first an activity. Okay, are you excited? Alright, very good. And this activity is connected to our next topic. I will group you into three, and each team will have a set of cards with various numbers written in them. You will sort the cards into three files: the real numbers, integers, and rational numbers. The team that finishes first and has the correct sorting wins will of course receive the highest score for this activity. Okay, so I will give you 5 minutes to finish this activity. Are you ready, everyone? Okay, very good. Okay, so your time starts now. Time's up, so may I ask one representative from the team one? Who is your representative? Okay, so Anna. Okay, Anna, what have you noticed in doing your task? Okay, very good. How about in group 2? Who is your representative? Okay, John. So John, how would you use the concept of real numbers to classify the examples you found? Very good answer. How about in team 3? Who is your representative? Okay, we have Maria. So Maria, what do you think is the difference between an irrational and irrational number, and provide an example of each? Okay, exactly. Very good answer, Maria. Your answers are all right. So let us proceed to our next activity, which is entitled Might Relay Challenge. Okay, so are you excited? Oh, it's nice to hear that you are all excited. So the mechanics of this game is that each team will participate in a dynamic across three stations representing real numbers, integers, and also rational numbers. At each station, a team member will tackle a mathematical problem related to their assigned number system and promptly record the solution on a whiteboard. Teams must ensure clarity in presenting answers. With a specified time limit for each round, teams strive to complete as many rounds as possible, earning points for correct solutions. Points will be deducted for exceeding the time limit. After rotating through all stations, the team with the highest overall score will be declared as the winner of this game. So, any question, class? Is it clear? Okay, very good. And now you may now go to your teammates. Listen carefully. I will read the direction. So solve the provided mathematical problem at each station related to your assigned number system on your whiteboard. Be precise and efficient in your calculations. Okay? Okay, let's start. Okay, so time's up. The challenge is done. Have you enjoyed our game? Okay, very good. At the same time, you have learned something from our activity.
Now, let's check your work and see which team got the highest score. Are you ready? Okay, I can see that you're so ready and excited. Okay, now let's start with the first question. What is the main objective of our math relay activity? Anyone? Yes, you, Joshua. Can you state what is the main objective of our math relay challenge activity? Okay, very good. Let's clap our hands for Joshua. Thank you, Joshua, for your wonderful answer. Let us now proceed to the second question. So, how did your team approach problem solving at each station? And did you find any particular challenges? Anyone from the class? Okay, you, Miss Anna. Okay, thank you, Miss Anna, for your wonderful answers. Let us give Anna a round of applause. Thank you, students. So the last question is reflect on the importance of teamwork in this activity. How did collaboration contribute to the success of your team? Okay, anyone from the class who wants to answer the last question? Yes, you, Mike. Okay, your answers are indeed correct. So now let's give Mike a round of applause. All your answers, everyone, are correct. So I think you will now have the idea what will be your next topic.
From the activity that we do today, so what do you think is our topic? Okay, Miss Shane. Okay, let us see if you guessed correctly. So our topic today is all about construction of the real numbers, set of integers, set of rational numbers. So let us read our objective first. Okay, all together. At the end of the lesson, the students are able to discuss the construction of the real numbers, set of integers, and set of rational numbers, describe the properties and relationships between these number systems, and lastly, apply the knowledge of these number systems in the problem-solving activities. Let us start with the construction of integers. So, The word integer is originated from the Latin word integer, which means a whole or intact. Integers is a special set of numbers comprising zero, positive numbers, and also negative numbers. The integers are represented by the symbol z. So, we have here the integers number line. So we have the zero, positive integers, and negative integers. So in the positive integers, we have 1, 2, 3, 4, and so on. And the negative integers, we have the negative 1, negative 2, negative 3, negative 4, and so on. Okay, so we denote integers with a z like this. There are many different ways to construct integers from the natural numbers, but the one that we are going to talk about uses equivalence classes. So say we have the number negative 3. Consider the equation x minus y equals negative 3. We cannot graph this like we would a normal continuous function, but we can graph it on a lattice of points where the x and y axes are the natural numbers. Our first point is here at 0 and 3. Our second point is 1, 4, and so on in a line with slope 1. Every ordered pair of points on this line has difference of negative 3. We can do the same thing for all the rest of the integers. To formalize this construction, we will define an integer k as an equivalence class of all the ordered pairs x, y such that x minus y equals k and x and y are natural numbers. Using the definition, we can create any integer as an extension of our previous construction.
Good morning, class. So I will be the one to discuss on how to construct the rational numbers, since we already been discussing on how to construct the set of integers. So now let's move forward to the rational numbers. But so before that, let me ask you, what is rational numbers? Anyone from the class? Okay, so I have 5 examples of numbers here, and I want you to identify whether these numbers are example of rational numbers or not. Okay, what is rational numbers? So when we say rational numbers, it is a type of real numbers where it is in the form of p over q, where our p there represented as our numerator and our q there represented as our denominator. But however, we need to remember that our q must not be equal to 0. So some examples of rational numbers are negative 1/2, 3/4, 5 over 8, and so on and so forth. Rational numbers also represented as the symbol of q. Remember that all decimals are not rational numbers. Those decimals that can be expressed as a fraction in which the numerator is an integer and the denominator is a non-zero integer can be considered as a rational number, or it is called as irrational numbers, but not all decimals. We find here the set of ordered pairs A and B is a congruent of x and y if and only if AY is equal to BX. That's how we define the equivalence relation if they are equivalent. So we can use this property. We need to use the 3 properties we have, the reflexive, the symmetric, and the transitive properties in order to know if the given set is considered as an equivalence relation or does have an equivalence relation. in reflexive property, we have A, B is congruent to AB. So it means that our A over B is equal to A over B. That's what we call the reflexive property. That's how we define the equivalence relation if they are equivalent. So we can use this property. And if we know that AB is a congruent of CD, therefore CD is a congruent of AB. And that's what we call symmetry. And in transitivity, we have here AB is a congruent of XY and XY is a congruent of CD. Therefore, AB is a congruent of CD. We are going to define A over B is the set of all CD congruent to AB such that CD is an element in the integers. So we're going to define also here our Q or our rational. We have the set of all A over B such that AB is an element or is in the integers. Help us eliminate the problem we had with the simplifying because, like for example, if I do 1 over 3 and 2 over 6, so this means that 1 over 3 and 2 over 6 are going to be the same. It is because if A over B is equal to 1 over 3 and 1 over 3 is congruent of 2 over 6, then we can conclude that A over B is equal or congruent to 2 over 6. The same as if we use 2 over 6. So if A over B is congruent or equal to 2 over 6 and 2 over 6 is equal to 1 over 3, therefore our A over B must be equal or congruent to 1 over 3. This eliminates the problem that we'd have if we didn't have the ability to simplify. But now that we are dealing with sets of all things that are simplified, we actually have now the rational numbers as you can see. And now it's time to define addition and multiplication, and it have now multiplication. So in multiplication, we need to multiply A over B times C over D. We need to multiply the numerator to numerator and denominator to denominator. So we have 1 times 2 and 3 times 6. So 1 times 2 is equal to 2 and 3 times 6 is equal to 18. So we have now the 2 over 18. And 2 over 18 can be turned into lowest form. We have 1 over 9 and 1 over 9 will be our answer. So 1 over 9 can also be turned into an ordered pairs of 1 and 9. So our 1 there is our numerator and 9 is our denominator. That's how we get multiplication in multiplication. So in addition, we also have A over D plus C over D. We need to multiply A times D plus C times B over B times D. So our A times D there is 1 times 6. So we can have 6 plus 2 times 3. Our CB is equal to 6. So 6 plus 6 over, we need to multiply the both denominator. So 3 times 6 is equal to 18. So we can come up of 12 over 18, and 12 over 18 can be turned into the smallest form of 2/3. So 2/3 as same as with multiplication, we can turn it into an ordered pairs, a set of ordered pairs, which is 2, 3. Our 2 there is our numerator, and 3 is our denominator. So we have 2, 3 as our answer in addition. Do you have any questions, clarifications, and violent reactions with regards of my discussion? If you don't understand something about it, you can ask me. Have you understand our discussion, students? Okay, very good.
Since we are now done in discussing about the integers and rational numbers, let us now proceed to our last discussion, which is the construction of real numbers. So real numbers is a comprehensive set encompassing both rational and irrational numbers. It can be defined as a union of both rational and irrational numbers. They can be both positive or negative and are denoted by the symbol r. Some of the examples of the real numbers are 26, negative 12, 6.99, 5 half, pi, and so on. How do we construct the real number line? Well, we use this thing called Dedekind-Katz, named after the German mathematician named Richard Dedekind. To quote from the textbook Very Good Explanation, the idea behind Dedekind-Katz is that real number x can be named by giving an infinite set of rationals, namely all the rationals less than x. So basically, the idea is that x may not be a rational number itself, but there is a sequence of rational number that gets infinitely close to x, because unlike the natural numbers and the integers, the rationals are infinitely close together. So no matter how close a given rational number is to some real number x, you can always find another rational number that's closer. So formally, a Dedekind-Kat is a subset x of q. The rationals such that x is not the empty set and x is not q. So x is neither nothing nor infinity. X is closed downward. That is, given rationals q and r, if q is an x or q is less than x and r is less than q, then r must be also an x. And finally, x has no largest number. It must be an infinite series that converges at some limit. As we can see, this supports our definition of real number x as the set of all rational numbers that is less than x. Therefore, the set of all real numbers is simply the set of all Dedekind-Katz. There is an alternative way to construct the real numbers using something called Cauchy sequences. It's a little harder to conceptualize, so I'm not going deep about it. But it is essentially a more general version of what we just did with the Dedekind-Katz. We defined a Cauchy sequence to be, first of all, a function from the naturals to the rationals. Another way to say this is a Cauchy sequence is a sequence of rationals, an ordered list with a starting point and a direction. Furthermore, this sequence of rationals must converge. It can't go off to infinity or oscillate back and forth forever. It must get closer and closer to some fixed number, which is our target, the real numbers. Using this construction, we cannot define a real number to be the equivalence class of all Cauchy sequences that converge to x. So the set of all real numbers is the set of all such equivalence classes. Any questions or clarifications about the construction of real numbers, the set of integers, and the set of rational numbers? None. Very good. Seems like you really understand the lesson today. Now, let us have another activity. Are you still sitting with your team? Okay, so listen. I have 3 folded papers. Each team will pick a representative to choose a folded paper. Inside the paper, there is a certain problem that your team must needs to answer. You only have 10 minutes to accomplish the task, and you will be graded with this rubric. Okay, listen carefully for the rubrics. So, for the understanding, 5. If you demonstrate a profound understanding of the problem statement and its complexities. 4. If you shows a solid understanding of this problem statement. 3. If you demonstrate a basic understanding of the problem but with minor inaccuracies. For the team collaboration, 5. If you exhibit seamless collaboration and effective communication. 4. If you demonstrate a good teamwork and communication. And 3, if you display some teamwork with breakdown in communication. For the time management, 5, if you efficiently uses the entire 10 minutes time frame. And 4, if you effectively manage time with minor delays. 3, if you adequately manage time but with noticeable inefficiencies. So that's all for the rubric. Please come forward for each team's representative to choose one folded paper. Okay, so your 10 minutes starts now. So work with your team and we will check that after 10 minutes. Time's up. So let us check your answers. So, congratulations everyone. Let's give a round of applause for the 3 teams for a job well done. So, here are your scores. So, Team 1 got 14 points. For the Team 2, you got 13 points. And the Team 3 also got 13 points. Congratulations. And now, please arrange your chairs and return to your proper seats. Okay. Any questions regarding our topic? None. Since you don't have any questions, it's time to test your individual knowledge. Okay, for your individual activity, please listen carefully for the questions. So number 1, given the sequence 1, 1.4, 1.41, 1.414, and so on, demonstrate how the sequence represents the construction of real number. Explain the significance of the terms becoming arbitrarily close to each other in the context of constructing real numbers. For the number 2, perform the following operations with integers: negative 5 plus 8, negative 3 times negative 4, and 6 minus negative 9, and discuss how these operations illustrates the properties and relationship within the set of integers. For number 3, consider the rational sequence 1/2, 2/3, 3/4, and so on. Determine whether the sequence is a Cauchy sequence and explain how its convergence relates to the construction of rational numbers. For the number 4, choose 2 rational numbers, perform addition and multiplication, and verify whether the results remain within the set of rational numbers. Discuss the closure properties of the set of rational numbers under these operations. And for the number 5, analyze the sequence 3, 3.1, 3.14, 3.141. Identify the pattern and explain how the sequence represents a contribution of real number. Discuss the significance of the sequence converging a specific value. That's all. Answer that in a one whole yellow paper. And good luck.
Please get a one whole sheet of paper for you to write your assignment. You will submit this assignment in the next meeting. Okay, so make sure that you have your answers.